Good morning, everyone. Today is our seminar, chemical engineering seminar series again. Now it's in October, so we have here with us Professor Dmitry Murzin. So a little bit about him. So he graduated for the bachelor. He graduated from the Mendeleev University of Chemical Technology in Moscow in 1986 with an honors degree. Okay. And then he did his PhD with Praserthdam at the Kharkov Physical Chemical Institute in Moscow in 1999. And then he did a postdoctoral in France and also Finland. And briefly, he has been working with the ASF until 2000, and then he joined as the board chair of chemical technology at Akademi University in Turku, Finland. So he has a lot of awards and he published many books. Some of you.
Yeah, that's not needed.
Yeah. Okay. So please welcome Professor Murzin. Okay.
Thank you very much. Yeah. Maybe you can hear me. Thank you very much, and I'm sorry for the delay because we went through the wrong exit at the shopping mall and started to look at the GPS navigator, and I put the wrong address, so they ordered it turbulent. So it never happened before. I told you, and now it's once again, I was not able to come on time. It's really a pleasure to be here. Professor Murzin came to Finland was a half a year ago, and then asked me to come to Thailand, and it's my second visit to Thailand. The first one was 16 or 17 years ago. It was just one day in Bangkok, and it was not enough. So what I'm doing now is just enjoying your culture, the atmosphere, and very good hospitality with Thai people and showing the visitors. So a few words about myself and the country. So the title of the talk is not directly 3D printing. So I will discuss in general the art of shaping. So how to make catalysts. And I will first talk about extrusion, and then we'll move to 3D printing. We'll try also to make the connection between extrusion and 3D printing. A few words about the city where I live and then the country. So the city in Finnish has the name Turku, and in Swedish it's Åbo. So it's the same city which has two names. And the reason is that Finland is a bilingual country. We have two official languages. One is Finnish language, which is not an Indo-European language. It's difficult to understand that. And then the second language is Swedish. And the reason is that Finland for a long time was a part of the Swedish kingdom. And 200 years ago, approximately, it became a part of the Russian Empire. And then more than 100 years, it's independent. So in Thailand, if I understood correctly, you have basically one season, which is for us summer. It's all the time summer. For us, it's a little bit different. So it's the same photo. Actually, the photo is not the same, but the angle is more or less the same. It's then the winter time. But something like that, with a lot of snow, can be even in April. Actually, we have relatively long winters. Sometimes in March there is no snow, and sometimes it can be also then even in the beginning of May. So just few photos of Finland. That's red currant, the berry which I have in my garden. I have several bushes, so I pick up those berries and then I will show what I make. This is the hare, or the rabbit, comes very often. So I live in the countryside, and then I have deers and rabbits and foxes coming from time to time. No wolves. One bear was seen like 400 kilometers, and then sometimes we have these large mooses or elks, with these huge horns. I have seen a couple of times in the vicinity of my house, and they are really dangerous. Just to repeat a little bit of what I was doing. So I have the degree in chemical engineering from Mendeleev University of Chemical Technology. Then did my PhD in Kharkov Institute with advisor, which Professor Temkin. I will say a few words about him. Then was a postdoc in France, in Strasbourg. Then spent some time in Finland 1 year. Then went to BSF to Ludwigshafen. Was dealing with different things, including not only research, but also technical marketing, startup assistance, design of CO2 removal units. And then at the end, it was a little bit of commercial activities, and that was too much for me. Then I moved back to Akademi. Few words then about my former PhD advisor, Professor Temkin. Some of you might know the Temkin absorption isotherm, or the kinetics of ammonia synthesis. Whatever, he did quite a lot also with not only in the field of kinetics, but in general physical chemistry. He is the author of Temkin explaining to Erwin Blattner and to Professor Frunkin, who has also his own isotherm, that the surface is in fact non-uniform. So the photo was taken in the late 40s in the same auditorium where I later on defended my PhD thesis and then Doctor of Science habilitation. Just to have a very light beginning of the lecture, a few words about my hobbies. That's I'm writing books, as you have mentioned. So the monograph on catalytic kinetics was published 2016, and then several textbooks, chemical reaction technology, formulation product technology, and then engineering catalysis. And that's also, these books reflect in a way the type of research what we are doing. So it's very much about kinetics, about catalysis, and then modeling of reactors and development of reactors. So my hobby is also to derive kinetic equations, and sometimes when I have nothing else to do, I derive these type of equations and publish them in reasonable journals. So that was about catalytic kinetics in non-confined space of acidic micro isoporous materials, where I was trying to derive a very general kinetic expression for catalytic reactions where we have different type of acid sites in micropores, in mesopores, or sites on the external surface. So that's just a little bit of what I am doing. And then you have seen the berries. So making jam is another hobby. And then the fridge is full with always, I would say, jars of jam. There's no place to put any food. And then another hobby is to paint the building, so the house brand new. A few words about the lab. So there were 3 or 4 slides about the laboratory, and then I move to the topic of the lecture. The name of the lab is Industrial Chemistry and Reaction Engineering. We have 3 chair professors. My chair is in chemical technology, and I have a colleague, Professor Salmi, who is very well known in the chemical reaction engineering community. The third professor, relatively young person, has his chair in process intensification. Then we have several, 2 associate professors, few tenured scientists, and then approximately 30 to 40% from really all over the world. Now I put 15 plus, but maybe there are 17 or 18, including Iran and Venezuela and Bangladesh, and I can continue. Few words about infrastructure. Professors visited our building. We moved to that building 3 years ago. So therefore everything looks brand new, and it actually it is new. This is the room where we have a lot of GCs. We have also several HPLCs that looks like a GCMS. This is a 2-dimensional GC. Another GC, we have quite a range of GCs. A little bit about other pieces of equipment, ball milling, infrared, UV, another infrared, surface area measurements, extruder, that I'm going to talk about that. Then also we have a 3D printer. So I will then focus on making the catalyst using these two methods. And then we have a lot of reactors. The typical size of our reactors is 300 milliliters. And we have actually plenty of them. There are a few reactors of a little bit larger size. And we have also reactors for fixed bed, for continuous type of operation. And there is one reactor system with 6 pickle bed reactors in parallel, which we developed the first version ourselves. So what you see here, everything was constructed and assembled by our laboratory engineer. So we have a very skillful laboratory engineer who then designs and assembles the different type of setups. Obviously, these mass flow controllers and pumps we buy. Reactors, sometimes we buy and sometimes we do it ourselves because we have a reasonable quality workshop in the building. And also reactors for different type of reactions, which we do under atmospheric pressure with less reactors, and then basic infrastructure for the spectroscopy, X-ray diffraction, Raman, and all the things. So, I think we are very well equipped. So it's time now to start with the main content of the lecture. The largest reactor, what I have seen myself, was or is the catalytic reformer with a height 70-something meters. So there are huge reactors out there in industry. And the problem is if we have a fixed bed reactor, then we cannot use small catalyst particles. Once I had a project with a French company, and they were dealing with hydrogenation of one organic compound, and they used the HQ reactor with the size of the bed, something like that. And then they put the very small catalyst powders, I don't know, it was 50, 60 microns, and the pressure drop across the bed was 70 bars, 70. We cannot afford that in industrial conditions. So this is the reason why we have to use something which is of relatively large size, or few millimeters or something like that. So then it means that then we have a problem. And from the point of view of pressure drop, we want to have something relatively large. But from the point of view of mass transfer and catalyst effectiveness, then we want to have something smaller. So what we put in industrial reactors quite often is then the compromise. So small is better from the viewpoint of mass transfer, and big is better from the point of view of pressure drop. So this is called the classical trade-off in reactor design. And that brings then us to understanding that the size of the catalyst particle should be large enough. Then we have to make that somehow. These are the examples of catalysts which I use industrially. This is 428 catalyst. It's the code of that for sulfuric acid production, which was or is made by BASF. And then I will later on mention the same type of catalyst which will be made by 3D printing. You will see the difference. So, large reactors, large scale production, potentially high pressure drop, then we need to have a shaped catalyst. A quote, I don't know from whom is this quote, maybe it's from myself. That's the most economic and commonly applied shaping technique is extrusion. So the first part of the talk will be done about extrusion. And the extruders, what we use and what you have, we also have one extruder. The extruders are different in the lab scale and the industrial scale. So what we see here is a 3-screw extruder for both like that. While in academia, typically it's just one screw. And that means quite often it's extremely difficult to do scaling up of the catalyst. This is a very general statement. I have spent some time in industry. I know how difficult in general is to do scaling up. Whatever it is, extrusion, simple mixing, impregnation, calcination. One example from not from my own experience, but from experience of my friend was when I was working at BASF. He was involved in scaling up and development of the catalyst, which was shipped 60 tons. They were shipped to South Korea from Germany, put inside the reactor, and then BASF was not able to fulfill the guarantee. And then these 60 tons were taken out from the reactor and shipped back to Germany. And the reason was that it was difficult to emulate the conditions of calcination. You have calcination ovens. You have calcination ovens in the lab. This is typically static air. When you do it in industry, there is a conveyor belt, and then you might have some fans, you might not have, so the airflow is also different. So just a simple unit operation like calcination, relatively difficult to scale up. I will also say later on a few words about extrusion. So this is a small-scale extruder which we purchased from China, and it's extremely cheap. The price was 700 euros, and the cost of shipping the extruder from Tianjin to Finland, including custom clearance, was 700 euros. So shipping costs are exactly the same as then the certainly you can make it more complicated if you measure also the pressure at the outlet of the extruder. Then, if you buy something like that from United Kingdom, it will be 20,000. You can make it as complicated as possible, and also with the proper cutting devices. Who knows what is that? Who was using it? You were using it. Because when I'm asking my students back home, typically nobody knows what is that. It's actually the domestic extruder, which I started to use at home. So this is me actually, I will be able to recognize. And this is my grandmother. She was my first teacher in extrusion. She taught how to do that. Because the then is very much the same. You also need to be careful with the composition of the extrusion mass. It's meat, you can add maybe bread, onions, or whatever you want to use. So maybe a little bit just water, smoother. So conceptually, what you have is then the paste, wet paste, and this is actually extremely important. What will the content of water? I will say a few words and maybe show one movie about that. So wet paste is fed through the screw transport system, and then the paste is pressed through the holes of the dies, and then the paste goes like that, and then by gravity falls. Typically, we might have a cutting device. So in industry, there's always a cutting device. In labs, not always, and then we cut. Therefore, quite often these extrudates, they have a little bit of bending shape because of that, because of gravity. So if we just use the powder and water, typically it doesn't work. We also need a lot of binders and additives to make the extrusion possible. So this is the slide what I'm using. It's after Javier Perez-Ramirez, a friend who works ETH in Zurich. He is also dealing with extrusion. And then he put the slide, the first part of that you see now. So the research catalyst that the majority of people in academia using contains just the active phase and the support. Very often it's like that. In reality, what you have the binder, maybe a clay. And this clay might have its own catalytic properties. And the amount of the binder can be 30–40%. So imagine you tailor-made your catalyst, which can be, for example, a zero line or a metal supported on zero line. You optimize it for a certain reaction. And then when you go to industry, you should make an extrudate, and then you use, for example, I don't know, aluminum. or a certain clay, it contains its own Lewis acidity. Or you use bentonite, it contains 3 to 4% of iron. That can be also catalytically active. And if you want to make an extrude, you also add then the peptizer, which might be, I don't know, nitric acid. It might be an acid which would also influence acidity. So it took really some time for me to convince the funding agencies to give me funding for studying this type of materials, the real extrudates. Because the referees or reviewers of grant proposals were telling that this is not important, it's just the active phase. And I was trying from different funding sources. At some point, I got funding from the Research Council of Finland, and I was lucky enough because one of the members of the jury knew me reasonably well, and then she thought, okay, let's give them a try. And there are not that many academic labs in general in the world who are interested in shaping of catalysts. There is one group, maybe Rutgers University in the United States. There are a few in Europe. I don't know how many are in Asia. Not that many, because there's no glamour in studying catalyst shaping, especially by extrusion. You cannot go to Science and Nature. You can go at most to some reasonable chemical engineering journal. But it's extremely important if you start to think about industrial application, industrial catalyst. People in industry, typically, they would not say anything about the catalyst preparation. I was working at BASF, and those who were not working in the catalyst or catalysis division would not even have the access to the plant making catalyst. Everything should be super secret. So all that, and on the other hand, I also should mention that the scientific basis for catalyst shaping, if you work in industry, they are also not that much interest. You don't really study rheology, you don't do it systematically, it works and that's it. So you have a recipe. Therefore, I also put in the title, The Art of Shaping. I will also say a few words how we could try to put more science in that. So this is an example of extrusion. What we have, you see, we put the paste and then we have some extrudates coming out. We don't have, once again, the cutting device, so we cut all that manually. So what are the parameters affecting extrusion? The particle size in the slurry should be small enough. Then operational parameters, mixing time, temperature typically is not really a parameter. Everything is done at room temperature. When you do extrusion of plastics, then it's done in the molten phase. So then you really need to melt the polymer. Here it's just room temperature. Water content, this is extremely important. I will show a few examples. Additives, the content and type. This is an example of extrusion where we have different content of water. 58% versus 55. You see a huge difference. Recently, I heard a story about an industrial catalyst, and I think I will tell the story. There was a company in Europe interested in making 4 tons of catalyst. And there was only one technician at that company who was able to do that. And it was not even about water, it was just about humidity at a certain amount. That humidity should be at a certain level. So that person, unfortunately, had some personal problems and was on the sick leave for 6 months. So not a single technician, another technician at that company, with basically the same qualification, was able to make this experiment. So the company had to wait for 6 months before they were able to deliver these 4 tons, which tells how sensitive this manufacturing can be to very small things. And once again, it was not just 5% of water, it was the level of humidity in making actually. This is a true story. So if it's too wet, then we might have something like that. That was the optimal content, and maybe if it's too dry, then I will not even able to make pH. Some other examples when we have different additives and we see that we can fail. And we actually failed many times. So, at some point, I was thinking that we can bring more science to this art of shaping by studying rheology. Rheological properties, how the paste goes through the extruder. And then I was using relatively well-known and established equations for non-Newtonian movement of liquids, if I could like that, or fluids. But the problem is the concentration suspensions, they have much higher concentration of the solid than even we are able to measure for different type of rheological measurement. The concentration of the solid can be 40, 45, 50%. And it's rheological measurements and even the theories which are behind these measurements, they correspond to the solid content maybe 15, 20%. So we started to measure, for example, shear stress as a function of the particle volume concentration, and this is something relevant for us, 35%. Then these linear expressions, which I mentioned before, they're not valid anymore. So we started, it's like that. So when you have high concentration of solids, it's not only about the rheology, it's also about the interactions between them, the solid particles, it's about the charge to the other parameters, which are influencing then the extrusion. I will give one example, just one example, and we'll discuss our experimental work in synthesis of menthol studied from citral. Just one example. And then I move to 3D printing. So this is an example of reaction network where we have several reactions, one after another. So we start with citral, which is an unsaturated aldehyde, and you see here the conjugation between the carbonyl group, the double bond, and then there is an isolated double bond in the moment. So what we do first, from citral, then we make so-called citronellal by hydrogenation of this double bond. It can be done over rhodium, ruthenium, or nickel. The first is hydrogenation of this unsaturated aldehyde, the double bond here. So we need to have a metal function here. The second step is cyclization of citronellal to isopolyol, and that requires some acid sets. Then we form isopolyol, and then the next step is hydrogenation of this double bond here to the metal. So in principle, we can have three steps, one after another, but it's also possible to combine them in make them as one pot. So we hydrogenate citral to citronellal, then the second step is cyclization, and then hydrogenation of methyls. What is the advantage of combining three steps together? I think the advantage is clear, that we save on capital costs. So instead of having three reactors, we have just one reactor, right? If we do it continuously. So this is the apparent advantage. Low capital costs. But then the downside is lower flexibility, which means that all three steps, they should be conducted at the same conditions. When somebody is telling you that one pot is very good, now, sometimes yes, sometimes no, because then we have to find a compromise, because the optimal conditions for each and every step might not be necessarily the same. So you might have changes in the pressure or whatever it would be, atmosphere or temperature. But in this particular case, for one pot citral transformation, it's possible to find reasonable conditions. And we started with this one pot synthesis many years ago, But a few years then decided to move from batch to continuous. This is the continuous system what we have. And when I go to the lab, I put the lab coat on just to give some sort of a good example to the students. Some of them, they don't want to put the lab coats, and I cannot tell them it's obligatory if I did not wear the lab coat myself. You see, we have 6 reactors in parallel, and this is just an example of the batch reactors. Or cascade of batch reactors is something which was used already several hundreds years ago. If you look at the impellers, actually, think about the shape of them. They are rather advanced, even according to the modern standards. So they were able to ensure efficient mixing even a few hundred years ago. So let's go now then from powders to extrudates. Yeah, the reaction which I mentioned is relatively simple, but in reality it's not that simple. Even citronellal to isopolyol results not only in one isopolyol, but in 4 of them. And then we can have also the mention of different type of diamonds. So the reaction network is much more complicated. I will even show one slide highlighting that. Few words about the binders, which type of binders we are using. So there are different type of binders available. I mentioned alumina or boehmites. We also use bentonite. There are also some binders which are more, I would say, inert if it's colloidal silica. Then and actually we moved at some point to study this type of binders because of thinking that they will not have acidity of their own. But one example I want to show is related still to bentonite. Bentonite is relatively complex. It contains different phases: kaolinite, illite, monokaolinite, and then, as I mentioned, it contains also a certain amount of iron. So we started just with mixing bentonite with the zeolite beta. That was just the starting point. So let's see. We mix them together and see what is happening. And we were using a very simple ball milling, even prior to extrusion. Surprisingly, we were able to publish this paper 6 years ago in Catalysis Science and Technology, just characterizing what is happening when you mix the binder together with the zero. What would be your expectation? So there is certainly a mechanical force involved here when you do ball milling. So the classical assumption will be that there is no influence of this mixing on the properties. And the answer is no. Just, well, this slide is very busy. I will try to guide you through. Acidity of the beta zeolite with here the ratio of silica to alumina 25. This is acidity of the neat binder. Okay? So one would expect that if we have a mechanical mixture made by this ball milling, then we will have just the acidity linear function of the concentration of the binder. That would be the expectation. In reality, it's not like that. So the concentration of binder, for instance, is 20%, and the acidity is much less than what we would be expecting. Just once again, mechanical impact of ball milling will influence acidity of your zeolite. And then we are going back to the starting point. So I mentioned that people are talking about the research catalysts, and they think that we just use a binder, and the binder is inert, and that's it. Once again, you fine-tune your catalytic properties for the research catalyst. You work in academia, and then you give your recipe to industrial chemists, and they are not able to reproduce your result, and then you blame them because they don't know what they are doing. But in reality, it's something else. Once again, it's just mechanical mixing. So morphology is changing when we add different amounts of bentonite. So we saw really differences. This is just one example. Now a few words about a very simple reaction. The one in the middle, where we have cyclization, where we need only the acid sites. Now we move to these compositions with the binders. Conversion, now I show the results in the continuous fixed bed reactor. So what we see here, the conversion depends on the concentration of, or the type of binder, the concentration of the binder. This is the first thing. The second conclusion what we made is that this is time-on-stream behavior, that the final conversion depends on the diameter of the extrudates. This is something what in principle we could anticipate. Well, you have smaller size, then you have higher catalyst effectiveness, where the chemical engineers here in the audience, they know everything about the Taylor model, so that is somehow could be anticipated. What was important, and that's actually another important conclusion from the point of view of scaling up, that the selectivity was not that much influenced by mass transfer. And this is actually an important conclusion, especially when we do scaling up in industry of reactions related to maybe fine chemicals or pharmaceuticals or fragrances, because there we are much more interested in selectivity rather than activity. That was also the first statement which I heard from my boss when I started at BSF almost 30 years ago. He told me that what we are doing here is trying to improve selectivity from 80% to 81%. Something like that. So selectivity is the key because it actually brings quite a lot of money. It's also savings on the downstream treatment and separation. So in chemical industry, it might be 1-2%. Selectivity is the key. If you go to oil refining, it might be 0.1%, and that brings you a huge amount of revenue. But here, at least that's good news for scaling up of this process, that selectivity or the ratio between the isotopables didn't change that much. In this particular case, what I'm discussing now, so we have the acid function, but we also need the metal function. So we make the extrudates, the catalyst pellets. It's important to have active, stable, certain porosity, should be the mechanical strength and size and shape. But also it's important where we put the active phase. And the active phase in this case is the metal. Because once again, we have hydrogenation, cyclization, and then hydrogenation once again. And hydrogenation then it's for the please come. The most interesting things are starting now. It's about the influence of the metal. For a very long time, there was some sort of an assumption that the closer the acid sites to the metal sites, the better it is. That was called the concept of site proximity or intimacy of active sites. And this is something which is used as an important concept in oil refining, especially in hydrocracking and in hydroisomerization, where you have the metal function and you have the acid function. So the idea is that they should be put close to each other, the metals and then the acid sites. Some years ago, well, already 9 years ago, Brian de Jong from Utrecht and Johan Martens from Leuven, they published a paper about the nanoscale intimacy, and they were trying to challenge this concept. So, summa summarum, the conclusions were that the acid sites should not be necessarily close to the metal sites. Why is that? So, they put it schematically here. So, platinum can be put on the binder. The binder is aluminum. While the zeolite with different acidity, the sites should not be necessarily close to the metal sites. What was the idea, or what was the conclusion behind? If the sites are too close to each other, then you might have deactivation, formation of coke on the acid sites, and that might influence the metal. Brian, who is a good friend, didn't use or didn't make extrudates himself. They purchased extrudates, commercial extrudates from Shell. And then they really had a challenge to introduce the metal either on the binder or on the acid side. So they had once again the ready-made extrudates, and I'm trying in a very special way to put the metal either here or there, either the binder or the zeolite. We made it slightly different because we have this possibility of making extrudates ourselves. So a few words then about the methodology. And we use this procedure for different types of metals, for platinum, for nickel, or ruthenium, we can do it for iridium. And the zeolite can be whatsoever, ZSM5, beta, MCM41. And then the bentonite, or saprolite, or heptabolite, or whatever, blue dots, whatever is the line. It doesn't matter that much. So the first idea is that what we do, then we have the power of the catalyst, then we do shaping by extrusion. So once again, this is the mechanical mixture of the catalyst means the zeolite. The zeolite, the binder, we do shaping by extrusion. We also add the organic binder, methyl cellulose, which is then calcined, so it's removed after calcination. And then we do impregnation of the metal. So we do impregnation then of the extrusion. This is one idea. The second, we have the mixture of the zeolite and the binder, and then we do impregnation. And then the next step is extrusion. The third option can be we just impregnate the binder, so there is the binder with the metal. Then we add the zeolite and then we do shaping. Clear. And then the last option would be impregnating the metal on the zeolite, adding then the binder, and then doing extrusion. You see, so there are at least 4 options. So it gave us much more possibilities than it was in the case of Brian de Jong, who once again used the commercial extrudates. We have published a lot of papers related to citral, menthol, or different type of extrudates, MCM41, Y, beta plus ciperolide, MCM41. So those of you who are interested can go into the details. Can see the details looking in the paper. I will just present few results, just to give some sort of an impression what would be the result. Once again, the scheme, the metal is used to hydrogenate a double bond. The acid sites are needed for cyclization, this one, and then this double bond moves to the terminal position, and then the final step is hydrogenation. So that looks very simple on paper. In reality, it's a little bit more complicated because it's not only one citral, it's a mixture of isomers. It's not one isopolygol, there are 4 isopolygols. Then we have 4 menthols. In reality, there are 8 if we think about optical isomers. But this is not yet the end of the story. We were interested in one, but if we continue, so it goes like this. Because we also have a lot of side products, the catalyst deactivate. We have then as we call functionalization, removal of then oxygen, and formation of pyramid. I mean, it's really quite complicated. So I wrote the research proposal, but there were other people who had to struggle with analytics. They managed to do that. I think I don't have that much time, so let's continue. So finally, we solved all the analytical problems. We did our experiments in the continuous system with 6 parallel reactors. And just, I mean, there are a lot of data, and that's not that important to look at the data. What is important is to look at the values of conversion versus time on stream. They're very much the same. So this is okay. But if you start to look at selectivity, you see huge difference. And this is the main message. So once again, not about the details. So there is a huge difference in the formation of isopolyrolls, in the formation of metals, depending on how we make the catalyst. And this is an important message for those who are dealing with scaling up. We really have to think where we put the active phase and how we make extrusion. So scaling up is far from being easy. Just the last slide, I think, about that. This is a trickle bed reactor. We had a lot of menthol and not that much of other isomers of menthol. And we have this ratio of isopropanol to isopolyrol to neo-isopolyrol like this. And then we look at the bench results, they were different. This is the main message. So there is a difference between bench and continuous. There is a difference how you introduce the metal. This is the main conclusion. Because once again, it doesn't matter what is the reaction. The last slide related to central to menthol is about MCN41 and cepiolide. So we were able to have reasonably high selectivity to menthol, approximately 60% by then selecting the preparation method, the type of the metal, and the type of the mineral. That was just the final slide about that. Then I move, I have maybe 15 minutes, if you allow me, about the 3D printing. So 3D printing then is another way of making the catalyst. It's a way to make new structures. We have a PhD student, Luca Mastroianni, who is very much involved in that. And he started this type of research in our lab. So the idea of 3D printing or additive manufacturing is then to make the manufacture the object layer by layer, layer by layer. So pressure drop in principle can be under control. We can have improved heat and mass transfer because we can design the structure in the way we want. So the starting point for us, or for me at least, was to have catalysts for reactions which are highly exothermal, that we were able to manage the heat. That was the starting point. Now we are using for other type of reaction, but at least that was the idea. So how to print 3D catalyst? There are several ways. We started with direct ink writing, where the ceramic paste, the catalyst, and the additives will go through the nozzles. We did that in collaboration with the Cultural Institute of Technology, and we had a problem. The problem is that the size of the nozzles is very small. So it means that we really have to go to 1 micron size, and that was really difficult. So we failed, despite all our efforts. So low resolution, slow printing, so we gave up. We went on to another concept. Quite often, myself and other people, when they talk about 3D printing, they criticize this methodology, saying that it's just for small pieces, that we would never able to produce tons. That is a relatively slow process. And extrusion, you can make hundreds of tons. 250 cubic meters of sulfuric acid catalyst are used in a normal reactor making sulfuric acid. Can we make 250 cubic meters? So that was the main criticism. Now I'm less critical and I would say more optimistic. After 2 years ago, after the October 2022, when BASF, the company which I used to work for, introduced this catalyst. And this is the catalyst for manufacturing of sulfuric acid. I was involved myself in selling hundreds of tons of sulfuric acid catalyst. And I was even inside the reactor making SO3 from SO2, taking samples. And so it is possible. It's not only for sulfuric acid, it's also for different types of sulfonation reactions. They are not making hundreds of tons, they are making a few cubic meters. But at least it's the industrial reality nowadays. These catalysts made by 3D printing. So we use the 3D printing with digital light processing. The 3D printer per se looks very simple. The one which we purchased costed $10,000. And now I think one can buy for half of the price this particular model. And then the cheapest probably would be a few hundred euros, something like that. Some of them are really very cheap. Then the resolution might be not what we want. So this is the person dealing with 3D printing, lady, extrusion lady, and this person was dealing with phones. And they were so excited to see the first results that they came to the lab, even were out wearing the lab coat, which is strictly speaking forbidden. But they were so excited to see for the first time that we were able to make this catalyst through 3D printing. So the idea is that we have a resin which is photocurable, and we use a UV light. So the process happens by layer, then we put the UV light, and then it somehow solidifies. So we will use a resin, right? And it's very easy to print polymers. Printing of these acrylic say polymers is not a problem. We start with the monomer. Either we buy something expensive from the supplier, we go to the local shop and then buy this type of monomers. Then we need to have a photoionizer. Then we need to have the whatever it is, alumina or silica or zeolite. Then the process goes layer by layer. Once again, we start then with the mixture of the resin and the cathodes. Then the next step is, after washing, we do calcination, which means that the polymer is burnt away. And that explains the challenges, or highlights the challenge. So if we have too low concentration of this monomer, too much of ceramics, then we are not able to print. And if we have too high concentration of the resin and very little of the ceramic, then after calcination, the body will not be mechanically stable. So it took approximately 1 year to come to some sort of a recipe to make this alumina. We started with aluminum. Now we also are able to print zeolites. Because otherwise, if it's excessive curing, we might have some uncontrolled polymerization, and we added some colorants. Then the next idea was to add isopropanol as a non-reactive diluent, evaporate propanol before the calcination step, and then we came to something reasonable with the optimal solid load in approximately it's here 60%. Yeah? So it's mechanically stable. And then even we went further to improve mechanical stability, because we tried with the clay binders like bentonite and metabolite, which I mentioned before. They didn't improve mechanical stability of this printed object. They were extremely fragile after the thermal treatment. So conventional strategies to improve the binding properties, which we use for extruded catalysts, wouldn't be applied. So we use then another strategy, and this is the, so after we do all that, it's the infiltration. So when we are coming to gamma alumina, we do infiltration with colloidal vermine. So we print the body, and then the next step is put some sort of a coating of boehmite on top of this gamma alumina. And then once again calcination. So we have 2 calcination steps. And that is the way to make something relatively mechanically stable. After infiltration, we improve dramatically the mechanical strength. The paper was published a few months ago in Catalysis Science and Technology, and it's one of the rare cases where the referees were extremely happy. Typically, those of you who are publishing papers in international journals, you know that the referees are completely stupid. They cannot understand what they are doing. They write some stupid things and stupid comments, you know. You know it yourself. This was a very rare case where we had very, I would say, smart and intelligent referees because they immediately understood that it's something new and exciting. This method, we're very happy. Which happens once again rather sadly. So we made them this impregnated materials. There's still a few slides left on the page. So this is how it looks like. And then the next step was to deposit, in this particular case, gold. We were depositing gold on gamma alumina on the printed structures. And we did deposition and precipitation with ammonia. The reaction is selective, well, it's actually oxidative dehydrogenation of ethanol. Yesterday, I saw that some of you are dealing with the same reaction, dehydrogenation of ethanol to acetaldehyde. We do it in a slightly different way. It's oxidative dehydrogenation in the presence of oxygen, which means that we need water, and then the reaction is exothermal, and it's much easier to do it compared to just dehydrogenation. So a very classical method of adding the gold. Some of you might know, or might be even involved in catalysis by gold, and you probably know the names of Haruta and Hutchins, who started this field at the end of 80s. But in reality, the first paper where this procedure was reported, published in 1815, more than 100 years ago, it was BP deposition precipitation with urea. And then the method was completely forgotten. So it was reinvented by Haruta some 70 or something years after the first paper was published. Which brings me to the important conclusion and the message to the young people: read literature. Try to read literature. There are pots of gold there. There were also clever people working 100 years ago. Because sometimes when I discuss with my students, if a paper was published before 2010, then it's complete rubbish. Yeah? But it's not like that. Young people sometimes don't understand that they were our predecessors were extremely clever. So we can print different type of architectures. Some of the designs are presented here. So we can print monoliths where the diameter is hydraulic diameter is the same because you have straight channels. And then we can also print structures where we can alternate or vary the cross section. That means that in principle we can have this additional mixing. We can then have changes in the backline number and also in the relevance number. And then one in principle along with the reactor, one can change the structure and put these pieces with different geometry. So I don't want to go into the details of the mathematics. It was sent to Chemical Engineering Science, the paper. I think it will be soon accepted, where we looked then at the modeling of this type of systems. We calculated also the Heckler number, and then came to the conclusion that the catalyst architecture can have an impact on the flow pattern, even if the Heckler numbers are relatively low. But still, we can have large differences. So the conclusion here would be that the variation of hydraulic diameter can enhance this local turbulence. And once again, if you think about a fixed bed reactor, one can make different type of profiling along the bed or the length of the tube, which opens quite a lot of new possibilities. So this is my crystal ball. I have a crystal ball. I left it at home, so I decided not to bring it with me. It's too heavy. But if I would look at the crystal ball and try to think a little bit about the future, it's difficult to predict the future. We will try. What we learned after COVID, that many companies, they started to use additive manufacturing to make different type of spare parts which were not available, which were not easily available. So we can use to make different types of spare parts, internals. One can even print the reactor. This is the reactor. This is a tubular reactor where we can have different type of inlets for different type of gases or liquids. And then here you see we can play with the shape. This is, if it's clear, it's the shape is like this. This is the place to make the catalyst. This is the place for like homogeneous contribution that was meant for oxidation of pharmaceuticals in wastewaters. That was very. So one can even think about bio-inspired catalyst architectures. It's just your imagination is the limit. And your imagination can be bio-inspired, can be something which is partially chaotic, can be structured. So it gives a lot of possibilities from the point of view of design of either catalyst beds and even a variation of these pieces along the reactor. So we are quite excited about these possibilities. So the final slide is the acknowledgement to people who were involved in the project. And we see here the names who were involved in extrusion and then in 3D printing. And with that, I would like to thank you for your kind attention. Questions, comments, suggestions? No, why not? No, it's after question.
First, thank you for your interesting presentation. I have a question about the last part, that was 3D printing, because we have other presented a few months ago. They are doing similar 3D printing, but I haven't seen people using metal 3D printers, because if you are working with the metal oxide as the catalyst, why aren't we using metal 3D printers? And they have much better mechanical stability. And then by calcination, by other heat treatments, we can convert them to the metal oxide. Or in this case, if we need the deposition, we can also do the deposition later.
This is actually a very good question, because we have also these pieces of metals which were made by 3D printing, not at our university, but we just outsourced them. We didn't do that much with the 3D printed metals. It's possible to work, but then what you need to do, you have iron, for example. And then you want to use as your catalyst, ruthenium, and then the best support is aluminum. What should you do first? You should do something with this metal. And it's basically the same type of approach. What you will do if you have metallic bones, metal monoliths, you need to first oxidize the surface. And that because you need to make a surface layer of oxide. So you oxidize either under oxygen or you use some acids. So this is possible to do. Then on top of that, you need them to deposit aluminum, which is also possible, but that might be tricky. And you need to do wash coating, a similar way as you will do it, for instance, with monolith. Or if you use, for example, carbon as the support, then you need to figure out how to deposit the layer of carbon. So that is another option. It's in principle, it's possible. We just have this 3D printing with the digital line. So lithography is easy for us, but there are other options when you start with the metal. I don't know exactly how flexible and the printing and in terms of also the structures, but that I don't know. But we had, we just got some pieces and really something with them, but once again, I don't know how flexible. Here we have a lot of possibilities for how self-we design. But this printed metals, once again, is another option.
Again, thank you very much for the presentation. I have a question regarding the different strategies that you use for placing either the metal part or the catalyst or the binder. When you use those four strategies, did you see if there was any change in the stability of the catalyst? Did you do like any analysis after the catalyst were used?
The example which I presented is about the reaction which we conducted at a relatively low temperature. It's 60, 70, maybe 80 degrees C. So we have initial period of deactivation, but otherwise the catalyst is stable. So this is not an issue. When we go to high temperatures, that might make the difference. Because when you do then the deposition, you might also change the cluster size, the size of the cluster. And that might also influence how stable that you may have different degree of sintering at high temperature. So in principle, this is possible. Or it can happen. In this case, it was not really an issue. It's the temperatures were rather low.
That's back for the extruded catalyst for C-draw to menthol. The reaction should be tickle-based. The tickle-based, right? Yes. Because of the extrude is quite big. I want to know that. I want to know the last side of the leg that you use for create the catalyst.
The reactor. The size of reactor, if I understand correctly, I mean, the question, so the size of reactor is something like that. It's the reactor size. The size of the catalyst was approximately like this with a diameter 1.5 millimeter. The diameter, is it correct? The problems with no. I don't think, because they also, the catalyst amount was not that high. I don't think that we had really problems with hydrodynamics. No, not in this case. We saw actually fine particles and also structuring of the band for another reaction. That was oxidation of sugars. And that we did in another reactor. It was a column reactor where how many grams were 10 grams? No, but I think we had the structuring of the bed. Yeah, we have the structuring of the bed, and so we start with packed in a random way, and then since the flow was like this, from the bottom down, we really saw the structuring. But we didn't see the fines. We have to take a photo like that. We take the photo.